told you. Keep together, keep quiet, and above all, behave. You're going to be seeing a lot of very expensive and delicate scientific instruments. I don't want any of you to break anything. And Fran, please put that game station away and show some interest.
What are you doing?
I'm beta testing a game my dad's making.
Beta testing? We do that, only we call it playing. Can I have a beta test with your game station? I think she likes it.
Sorry we're late, Professor.
Don't worry, don't worry. And please call me Charlie.
Thanks, I'm Ruth.
Hi, Ruth.
Right, Charlie, is going to show you a scanning tunnelling microscope. It allows you to see right down to the level of atoms.
OK, thank you very much, Ruth.
OK, good morning, everybody, and welcome to the STM suite. Now, before we go any further, who knows what an atom is?
Aren't they the smallest things that anything can be made of? A bit like little balls that are stuck together.
That's right. But what are atoms made of?
Yeah?
Atoms are a bit like a solar system.
That's right. But what's in the middle where the sun should be?
Protons and neutrons.
That's right. And what goes around the protons and the neutrons?
Electrons.
Exactly.
That's the picture that we have of atoms. A bit like this picture we have here on the screen. So here we've got the negative electrons orbiting the positive protons and the neutrons.
Wow!
And the
I just got down to level 2. Never done that before.
The trouble is, this picture isn't quite right.
Because at the so-called quantum level,
Things aren't quite like this. But this picture will do for now.
and I'm going to show you some pictures.
Looks like something for a
of what
really
the
cool
surface
computer game.
really looks like.
Can't quite see it though.
If we push the probe very close to the surface, we can actually pick up atoms and move them around.
The point that I'm trying to make is that atoms are very,
Connect your
very
game
small.
station to the screen.
In fact, they're so small that you could take 20 million
Don't be
atoms
stupid.
side by side.
What? You mean you can't?
And in a single grain
Of course I
of
can.
sand, there will be a
But-
million atoms.
But nothing, hold that.
Where are we?
I'm really, really sorry.
I don't understand. Harry, Fran, do exactly as I say. Very slowly get behind me. Whatever you do, don't look round.
It's alright, I think it's dead.
No, they're very much alive. But don't worry, they're moving far too slowly to be of any danger to you. Welcome to my very own virtual reality domain. Sorry, just a little hologram joke.
Charlie, what's happened?
Well, I guess these two budding scientists here have managed to hack into a virtual reality program I'm working on. Here, let's have a look. Very nice device. Not seen one quite like this. Yes, you've hacked into my virtual world, and I see you're on level 2. That means you've been scaled down by a factor of 5,000.
Scaled down? So we're still on Earth, but smaller?
Yes, but on the floor. These are dust mites. The trees, human hair and bits of fluff. The boulders, just dust.
But why is everything so still?
Well, it's a quirk of the program I haven't been able to fix yet. We're 5,000 times smaller, but time's flowing 5,000 times more slowly. It can be handy, though. A second up there in the lab is over an hour down here. It's great for coffee breaks and a bit of peace and quiet.
So they won't be missing us in the lab?
Oh, not for a while yet.
Oh, the sky is so red. It's like Mars.
That's the light being scattered by all the dust in the atmosphere.
I hope you don't mind me asking, but why are you dressed like...
Like a cowboy?
Yeah.
No, don't ask. My research students wrote this bit of the programme. They thought it would be a good joke to dress me like this. Well, to be honest, they gave me the choice of this, or this, or this. I thought this was the most practical, so now I'm destined to walk through eternity looking like Jesse James.
What's that dust mite eating? Looks like a giant crisp.
Just bits of old skin. Human skin.
Ugh, gross.
Charlie, what are these?
Bacteria. E. coli, to be precise. The sort of bacteria that give you an upset stomach.
Cool. Come on, Fran, let's go check out what else there is.
It was you checking things out that landed us here in the first place. Be careful.
I know. It's okay, miss. You can't get hurt. It's virtual reality. Nothing is real.
Ooh. Unfortunately, my program's a little bit more reality than virtual. I'm sorry, it's another bug. I should have said.
Very fetching.
Don't worry, they're just grains of pollen.
Charlie, what's that?
A spider's web.
What, like some giant killer mutant spider?
No, just your common garden British spider.
But how big is it, miss, compared to us, I mean?
Well, I'm sure Charlie will back me up on this. If we talk about a spider with, say, 2 centimetre leg span, at this scale, the legs would be about 50 metres long, and the spider's body would be about 25 metres across.
Oh, I don't like spiders.
I don't when they're that big. And I think there's one coming now. You better dial up the next level, Fran, and quickly.
Where are we, Fran?
On the next level, like you said.
Whoa, it looks like some kind of space city.
Harry, get away from the edge.
Whoa. Whoa.
Floor's getting really warm, miss.
Where's Charlie?
Well, this is where you got to. I did say go down 2 more levels, didn't I?
No.
Oops. Still, you found an interesting place to visit. Interesting, but a little bit dangerous.
Where are we?
We've shrunk another factor of 1,000, so we're down on a silicon chip. In fact, I wouldn't be surprised if we're not inside Fran's game station.
Charlie, why is the floor getting so hot?
Well, these walkways are part of the electric circuit of the chip. And as electrons flow down here, the ground gets hotter. And it's probably going to get a lot hotter yet. I'd dial the next level if I were you, Fran.
I recognise this. We're on the surface of the piece of copper that Charlie showed us on the STM screen.
Didn't see that.
Well, you can see it now. Miss, what are these things?
The copper atoms Charlie was talking about, I guess.
He's over there, let's go and ask him. Hi, Charlie.
Hi! What kept you? I've been waiting here for hours. Never mind, though, you're here now. Welcome to my favourite virtual landscape. This is where the real world meets the quantum world.
So we've shrunk by another factor of 1,000 from the silicon chip world.
Exactly right. In fact, we're 5,000 million or 5 billion times smaller than we were. Thanks to my program, time's running 5 billion times more slowly. So we could be here forever and nobody would ever miss us.
Those look like oxygen molecules.
Yes, and nitrogen. And there's a carbon dioxide molecule. In fact, all the ingredients are the air.
But if those are air molecules, what are we breathing?
And how can we hear each other?
Virtual reality.
What's all this about?
I think it's time for a physics lesson, Ruth. Do you want to do the honours, or shall I?
We haven't covered this in class, Harry, but down at this level, things are better described by something we call quantum physics. Now, can you remember what particles are?
Very, very small things.
Exactly. Well, in quantum physics, things we usually think of as little particles, like the electrons that orbit around the atom, they sometimes seem to behave as waves instead. It's called particle-wave duality.
So these ripples are...
Electron waves?
Yes, these are the surface electrons that have broken free of the atoms they were orbiting.
Why are they so ghostly?
Because the other strange thing about the quantum world is you never really know where anything is, only where things are likely to be, and even then not very well. Where the ripple of the wave is biggest, it's likely that something like an electron will be found there. That's why they're called probability waves.
So, these ripples are telling us there's electrons moving around here somewhere.
Yes, but we don't know where exactly. Because the other strange thing about the quantum world is that you can't know where something is and how fast it's moving at the same time. It's called the Heisenberg uncertainty principle.
It's called rubbish. How can something be a particle and a wave and be here but not here?
Don't be so rude.
No, Harry's right. It does sound like rubbish. Even Einstein didn't believe it all. Quantum physics doesn't make much sense at first, but it really does work. In 100 years, nobody's ever been able to find anything wrong with quantum theory.
Are those electrons, miss?
Yes, photoelectrons. When each particle or quantum of light, which we call photons, hits the surface, it gives all its energy to a single electron. And if it can give enough energy, the electron can break free from the surface and escape.
It's called the Photoelectric Effect. Einstein was the first to explain it over 100 years ago, and that's what helped start the quantum revolution.
Blue photons are really energetic, but as you go down through the rainbow, the photons have less and less energy. By the time you get to red, the photon doesn't have enough energy to make the electron break free from the surface. Where are the photons?
There.
I always imagined to be tiny bundles of light.
So did I, but on this scale, they're nearly 4 kilometres across. Oh, I've caught an electron. But it keeps tunneling through my hands and escaping. That's another quantum effect.
Nah, it's just because you're a hologram.
No, it isn't. Here, catch. You see, Harry, you can trap an electron and try and keep it in one place. This is called localizing it. But as soon as you let it go free, it turns back into the probability wave again.
Cool.
This world is really very beautiful. What's that over there?
I was hoping to show that to your class, but I lost it on the surface. It's a carbon-60 molecule, Buckminster fullerene.
A buckyball! Harry, Fran, look at this.
What's a buckyball?
Form of carbon. Carbon usually comes as diamond or graphite. You know, the lead in your pencils. But this is a new type of carbon. It's only discovered recently.
It's named after Buckminster Fuller, the famous architect. But most people call it a buckyball because it's exactly the same shape as a soccer ball, but with a carbon atom in every corner.
Harry, Fran, get out of there.
Look out!
Ah!
Come on, let's go and take a look at my handiwork over here. So walk up to this. I might jump over it. Come on, come on.
Whoa! Look at that spike! It's huge!
That's a scanning tunneling microscope probe, Harry.
What are those things it's sucking up? No, wait. Let me guess. Electrons, right?
Have you seen the electric current you talked about in the lab?
That's right. In the lab, we measure about 10 billion electrons a second. But because my program slowed down time, we're only seeing about 1 or 2 a second here.
Charlie, look in here.
Oh, you found the standing waves.
Standing waves?
Yes, this corral of atoms that I've built have trapped the surface electrons inside. So the probability waves can't escape, so they appear to be standing still. Come on, let's have some fun with them. Climb over. OK, try over there, Fran. And there.
What happens if we break open the wall of atoms?
Try it and see.
You could help, Charlie.
I can't, I'm just a hologram.
But you caught an electron.
It was worth a try. OK, I'm coming. I wouldn't do that if I were you, Harry.
Harry! What are we going to do, Charlie?
Dial the next level, Harry. Sorry, I didn't mean to startle you.
I'm just trying to take it all in. It's stunning. I guess this is an atom.
Yes, we've shrunk by a factor of 1,000. We're now 5 million times smaller than we were in the laboratory.
But everything's made of atoms. But there's nothing here. Nothing at all. Nothing. Absolutely nothing.
Almost nothing. These clouds are the probability clouds of the orbiting electrons. The thicker the cloud, the more chance there is of finding an electron there.
But Miss, you said that the electrons go round the atoms, like the planets go round the sun. But instead of the sun, there's a nucleus.
That's an easy way of visualising the atom. but at quantum level it isn't quite right. We can only talk about the probability of finding the electrons. So we have these probability clouds.
OK, I get the probability bit. But where's the nucleus?
It's there, in the middle of the atom.
Where?
There. It's over 200 metres away, so you can hardly see it. But at this scale, it's only this big. But nevertheless, almost all the weight of the atom is concentrated in the nucleus. Don't you think it's interesting that almost everything you know in the real world is made up almost entirely of empty space?
More spooky than interesting.
Charlie, can we go see the nucleus, please?
I think you've seen enough for one day.
Oh, it seems a shame to come this far and not see the final level.
Well, OK then, but there may be problems. Serious problems. Well, you wanted to come to the nucleus. Here you are.
1,000 times smaller.
That's right. We're 5 million billion times smaller than we were in the laboratory. And the nearest nucleus is 500 kilometres over that way.
Where are all the protons and neutrons you were talking about?
They're here, but in the nucleus, they lose their individuality. So the nucleus is a little bit like a drop of liquid, made up of all of the protons and the neutrons.
Charlie, what's happening to Fran?
I thought this might happen. Particle wave duality. She's turning into her own wave function and delocalizing. Because she's the lightest, she's starting first.
Can't you stop it? It's happening to me now.
And me?
Fran, if you can still hear me, you know what to do.
The copper, and I've made a perfect ring of atoms. In fact, well, I thought it was perfect. One atom seems to be missing. But anyway, time's running out. You've got to move on to your next demonstration now. Our technician Deirdre will take you along to that. Thank you very much indeed for coming.
Thank you.
It's been a pleasure. You've got a really nice class. And I'm sure there are one or two budding physicists here. With that game station of yours, I'm sure you're going to learn a lot more physics. You could say you've got your very own pocket professor.
Fran.
What are you going to do with that?
Keep it.
What do you mean keep it? You can't even keep hold of it.
Of course I can.